Assalamualaikum and hi everyone. In this video, I want to summarize Chapter 3, Elementary Topology, which included in Course Learning Outcome CLO2. This chapter divided it into 3 subtopics. The first one is cardinality, which we will discuss how to analytically count elements in a set. In subtopic 2, we define interior points of a set and use the definition to define and discuss the properties of open and closed set. And the last subtopic deals with combination points of a set. Before we move to the first part in this chapter, cardinality, we will look at the elementary properties of functions. First, if A has many B, it is not a function. If B has many E, then it is general function. The function is said to be injective when B cannot have many A. The next figure shows every B has some A, so it is a surjective but not injective. And we have a property called bijective, which is one-to-one function, where it is perfectly A to B. This means that the function is injective and also surjective. For equivalent sets, let S and T be two sets. A set S is called equivalent to set T if and only if there exists a bijective function, which is one-to-one and onto. Now look at the definition of cardinality. Set S is finite if and only if S is an empty set, or the set 1 to n equivalent to S for some n in natural number. Otherwise, S is said to be infinite. Set S is denumerable if and only if natural number is equivalent to S. The cardinality of a denumerable set is denoted by alif null. Next, if it is finite or denumerable, the set is countable, and if it is not countable, the set is uncountable. By the above definition, it implies that two equivalent sets have the same cardinality. Finite set is also called finitely countable set, and denumerable set is also called infinitely countable set. There are a few terms in this subtopic. The first one is sequential criterion for countability, which states that a non-empty set is countable if and only if its element can be enumerated as distinct terms of a sequence. The second one is the union of two countable sets is countable. Thirdly, the product set n by n of positive integers is denumerable. The set Q of rational numbers is denumerable, while the set QC of irrational numbers is uncountable. The next theorem states every subset of countable set is countable, and the set R of real numbers is uncountable. Proceed with the next subtopics, interior points, open sets and closed sets. Let S be the subset of real number. A point X in S is called an interior point of S if and only if there exists an epsilon greater than 0 such that the open interval X minus epsilon, X plus epsilon is entirely inside S. A subset S of real number is said to be open set if and only if each of its points is an interior point. And a subset of real number is said to be a closed set if and only if its complement is an open set. In this subtopic, there are a few theorems that we need to know. The first one, if S is an open interval, then it is an open set. The union of any number of open set is an open set, and the intersection of a finite number of open set is an open set. Next, if S is a closed interval, then it is a closed set. Thus, the intersection of any number of closed sets is a closed set, while the union of a finite number of closed sets is a closed set. The last subtopic in this chapter is about accumulation points. By definition, let S be the subset of real number R. A point X in R is called an accumulation point of S if and only if for every epsilon greater than 0, the open interval X minus epsilon and X plus epsilon contains another point of S different from X. That is, there exists Y such that Y is in the open interval intersect S with Y is not equals to X. Next, the set of all accumulation points of S is called the derived set of S and is denoted by S prime. A point of S which is not an accumulation point of S is called an isolated point of S. Now we are going to talk about the theorems for accumulation points. The first one, the derived set of the open or closed or neither interval AB is the closed interval AB. The second one, if X is an accumulation point of S, then for every epsilon greater than 0, the open interval X minus epsilon and X plus epsilon intersect with S contains infinitely many points of S. The next theorem states that a subset S of R is closed set if and only if S prime is the subset of S. Next, a non-empty closed and bounded set of R has a maximum and minimum. And the last one, Bolzano-Weierstrass theorem, which states that if a bounded subset of R contains infinitely many points, then there exists at least one point in R which is an accumulation point of S. Move on to the last part of this video, where we are going to talk about the example of subtopic 3.2. Determine whether the following set is an open set or not. So first, the interval AB is not open, since not all of its points are interior points. We could say that the point B is not an interior point of AB, since for every epsilon greater than 0, the interval B minus epsilon and B plus epsilon is not a subset of AB. Therefore, with arguments similar to the proof of theorem in the subtopic 3.2, which state that if S is an open interval, then it is an open set. So we find that the interior of the interval AB is the open interval AB.
That's all from me. Thank you.